Today, we're jumping into something that, well, it really divides opinion. Nuclear power.
It definitely does.
Is it this crucial clean energy fix we need? Or is it actually a massive global threat we should just avoid entirely?
Yeah, the sources we looked at really show both sides.
Exactly. It's a big role in decarbonization, energy independence, but then you have the real concerns, safety, waste, weapons proliferation. It's complex.
It is. So our mission today really is to try and cut through some of that noise.
Right.
We'll dig into the science, look at the actual risks involved, and also some pretty remarkable advancements. The aim is to give you a clear, balanced picture.
Okay, let's start with the basics then, the science.
Yeah.
Fundamentally, there are two main ways to get energy from atoms, right?
That's it. You've got nuclear fission first.
Yeah.
That's what powers current reactors.
So that's splitting heavy atoms, like uranium-235.
Exactly. You split those atoms, release heat, make steam, turn turbines, generate electricity. Standard stuff in a way.
And the other one is fusion, the sort of holy grail.
That's the future potential, yeah. Combining light nuclei, think hydrogen types, deuterium and tritium. Basically trying to replicate the sun, but, contained.
How do they compare energy-wise?
This is where it gets really interesting. Fission gives you a lot of energy per reaction, sure. But fusion, per kilogram of fuel, it could potentially yield 4 times more energy.
4 times? Wow. Why is that?
It's about density. Fusion fuels just pack in way more energy-producing particles. And here's a key thing, the waste. Fusion mainly produces helium, which is harmless, and some short-lived, low-level radioactive stuff. Very different from fission's long-lived waste.
Okay, that's a huge difference.
And maybe the biggest point, safety. Fusion has what we call inherent safety.
Meaning
if the conditions aren't exactly right, the reaction stops. The plasma cools down. No meltdown possible. It's fundamentally different from fission in that respect.
That's a game changer, potentially. Okay, so putting fusion aside for a moment, let's look at current nuclear, fission, and its environmental plus points. It's often called clean energy.
It is, operationally at least. Virtually zero CO2 emissions when it's running. It provides nearly a third of the world's carbon-free electricity already.
And that's just operations. What about the whole life cycle? Building the plant, mining fuel?
Even then, it's incredibly low. The Uranium Economic Commission for Europe did the math. They reckon it's the lowest of all low-carbon options. Something like 5 to 6 grams of CO2 equivalent per kilowatt hour.
That's remarkably low. Lower than solar or wind life cycle emissions.
According to that UNESCO estimate, yes. Plus, think about efficiency. Land use is tiny. A big 1,000 megawatt plant needs just over a square mile. Compare that to solar or wind for the same reliable output.
Much bigger footprint for those.
Absolutely. And the fuel itself is incredibly dense. Get this. All the used fuel the U.S. has produced in, 60 years. It could fit on a football field, stacked less than 10 yards high.
That really puts the waste volume in perspective, doesn't it? Compared to fossil fuels anyway.
Totally. And it provides that steady 247 power, dispatchable power, which the grid really needs for stability. You can't always rely on the sun shining or the wind blowing.
True. But, okay, let's face the elephant in the room. The history. Chernobyl. Fukushima. Those cast long shadows.
They do. And they were terrible events. Chernobyl was a very specific, flawed Soviet design coupled with, human error. Fukushima was triggered by a massive natural disaster leading to safety system failures. Not operator error in the same way.
Important distinctions,
Yeah.
but still scary.
Of course. But here's a vital statistic. Globally, we have over 18,500 cumulative reactor years of operation. And in all that time, only those 2 major accidents have occurred.
Only 2.
Only 2, resulting in significant off-site releases. And crucially, outside of the Chernobyl first responders and initial victims, there have been no public deaths directly linked to radiation exposure from commercial nuclear power operations.
That's actually quite surprising given the perception.
Perception is key. Let's tackle some myths. Can a plant explode like an atomic bomb?
I think many people worry about that.
Scientifically impossible. The fuel isn't enriched enough, the physics just don't work that way. And radiation. The average American gets about 0.005% of their annual dose from nuclear power.
0.005%.
Yeah, you get more from a cross-country flight, or even get detectable radiation from eating a banana because of the potassium in it.
Less than a banana. Okay, that's memorable. What about the waste then? Even if the volume is small, it lasts a long time, right?
It does. High-level waste is long-lived, no doubt.
Yeah.
But it's only about 3% of the total waste volume. And here's something often missed. About 96% of what we call spent fuel can actually be reprocessed and reused.
Recycled, basically.
Exactly. And for the final disposal of that small amount of high-level waste, deep geological repositories, DGRs, are scientifically sound solutions, burying it deep underground in stable rock formations.
So the technology exists.
The technology is well understood and proven. Finland is actually building one right now. The main hurdle tends to be public and political acceptance, finding a community willing to host it.
Right. Politics, not physics. Now, you mentioned advancements earlier. How is technology making newer plants safer?
We're seeing designs with passive safety systems. These rely on natural forces, gravity, natural convection, not external power or pumps, to cool the reactor in an emergency. They fail safe, essentially.
Like small modular reactors, SMRs. We hear a lot about those.
Precisely. SMRs often incorporate these passive features. And overall, modern designs are estimated to be maybe 100 times safer than the older generations. Accidents like Fukushima are just far, far less likely.
100 times safer. That's significant.
It is. And the whole industry operates under incredibly strict international and national regulations, the IAEA, national bodies. They learn lessons constantly.
Yeah.
After Fukushima, for example, the FLEX strategy was brought in, adding extra backup equipment, defense in depth.
Layers of safety.
Many layers. And you know what? Public opinion seems to be shifting too.
Right.
Driven by climate change concerns, maybe. Support in the U.S. hit 75% in 2024, which is quite high. People are seeing the tech and safety improvements.
So wrapping this up, where does this leave nuclear power in the energy future?
Well, it has this unique combination, doesn't it? Reliable, always-on power, carbon-free, very high energy density. It really seems like an essential piece of the puzzle for a sustainable energy mix.
It does make you reconsider things. It's not a simple good or bad.
Definitely not. And that leads to the final thought for you, listening. Challenges remain. Absolutely public acceptance for waste sites, managing proliferation risks, the upfront cost. But with ongoing innovation, strong oversight. Nuclear seems poised to play a bigger, safer role in meeting energy needs and climate goals. So the question is, what stands out most to you from all this? What's the biggest takeaway?
Science.